Hello everyone, my name is Rafael. I am a postdoc at the University of Liverpool, and I don't work in quite as many hubs as Michael does, but I do work on Ring and Fairspace. And in this presentation, I'm going to talk about an interface for programming verifiable autonomous agents in ROS, the robot operating system. So we wanted to develop an interface for integrating verifiable autonomous agents with ROS. And to achieve this, we use the Gwendolen agent programming language. This language is developed by Luis Dennis, which is a co-investigator in Ring and part of Liverpool here. So with this interface, we want the agents to be able to send commands to the robot, as well as receive the sensor feedback from it. And of course, we want to verify the properties that are related to decision-making of the robot. This has been recently published in the European Conference on Multi-Agent Systems. Okay, but why do we want to use agents? There are several reasons for that. For example, we may want some explainability, which can be provided by the reasoning cycle of the agent. And I will show you an example of a reasoning cycle in a few slides. We may also want to separate the high-level decision-making from the low-level control of the robot. And more importantly, the Gwendolen language allows the agent programs to be directly verified using a model checker. Now, this is very important because some of the other techniques for verification that we have usually are based around building a model of a certain component or aspect of a system. Now, this can be a little bit tricky because we can't be 100% sure that the model actually relates to the code that is being executed. So by using the agents, and verifying the agents, we are running and verifying the code directly in the system. But as Michael mentioned earlier, there are several other parts of the system to make it a whole. So decision-making is only a small part of it. We still need all the others, so motion planning, image classification, and task planning, and so on. And for each one of those, there will be a wide different range of verification techniques that can be applied to them. But in this talk, I'm going to be focusing only on the agents. So I will give a brief background on autonomous agents. And here we have a very broad overview of what an agent, a rational agent, looks like. It interacts with the environment by receiving some perceptions. And this goes into the question mark box, which is the reasoning cycle of the agent. And then based on that, he does some computations and chooses some actions to execute in the environment. So very widely accepted model in the autonomous agents community is the belief, desire, and intention model. So in this model, beliefs represent the information about the world that the agent believes in. Desires are the goals of the agent. And intentions are steps on how to achieve these goals that represent also the commitment of the agent. So for example, here, the input is provided by the sensor, so some perceptions come in. They go into a belief revision function, which processes these changes in the environment. And then it updates, removes, or adds new beliefs to the belief base. This can trigger the option generation function, which is responsible for updating the desire base with new goals. So all of these changes go into a filter, which updates the intention base. And finally, the action selection function will pick an action to be executed as the output. So here's that example of the reasoning cycle. As you can see, it's very complex. So I'm not going to go into detail on what exactly is going on here, but I wanted to show it to you just so we have an idea of what a reasoning cycle looks like. And also because sometimes if you just look at the agent program, especially if it's a simple example, you may think, oh, but it's just a bunch of if and else statements. Well, the code may look like that, but there is actually a lot going on behind the scenes of the agent. So now I'll talk about the interface itself. So we can use agents in ROS. The interface is implemented as a Gwendolyn environment. This is pure Java code. And it connects with ROS Bridge using the WebSocket protocol. So ROS Bridge is a ROS library that uses JSON messages, and these are automatically translated from ROS messages. So the flow would be something like if ROS wants to send something to the agent, then the ROS will send a ROS message to ROS Bridge, which will translate it to JSON. Then it sends to the interface, which picks that up and translates from JSON to Java, which the agent can understand. And the same thing goes through the other way around if the agent wants to communicate with ROS. So this is the constructor of the environment, which just connects the agent to ROS Bridge. As you can see here, we are using localhost, which means that the agent is embedded or is supposed to be embedded in the hardware of the robot. But it could also be used remotely, although that may be adding some delays. So the next thing that we need in the interface are two things actually, which are the subscribers and the publishers. So we are able to communicate with ROS and interact with it. So as far as subscribing goes, it's completely transparent to the agent. Here we have an example of a subscriber. And here we are subscribing to the topic ROS to Java. And we need to specify the message type of that topic, which in this case is just a string. There are other optional fields in the subscriber, but they are the same as in any ROS subscriber. Then we have the publisher. We use the publisher inside the execute action environment in Gwendolyn. So here we have an example of it. And inside this method, the only thing we do is matching name of actions to the actions that we want to describe. In this case, we have the hello ROS action, which is calling our hello ROS method. And here we have the example of the hello ROS method. We create a publisher. We, again, specify the name of the topic. In this case, it's the other way around because we want to send something from Java to ROS. The type of message, which is, again, a string. And then the object that is used to connect, which is the bridge object. And for the action itself, this is just a simple example, which the agent sends 100 strings to the robot. Right, so if you look here, we have the primitive message of type string, and this is equivalent to the ROS message standard from the standard messages package. So in this table, we have on the left many different standard ROS messages, and on the right, the equivalent message in the interface. So if we want to make a new ROS message ourselves, we need to then implement what it means in the interface, so they can be translated from one to another. But it's pretty easy to do so as long as you know a little bit of Java. So now I'll show you an example. In this case, we are using the Gazebo 3D simulator, and we have a turtlebot. And we want the turtlebot to autonomous patrol 4 different waypoints. So it should go to A, then B, C, D, and A in that order. This is the code for the agent. As you can see, it's quite small. We start by defining the name of the agent, turtlebot3. Then we have a list of initial beliefs. In this case, they are the 4 different waypoints and the respective coordinate of each waypoint. And then we have the initial goals, which in this case is to patrol waypoint A. So what happens here is that when the agent program executes, we will have the addition of the goal patrol A. This will trigger the plan, so the first plan here on line 18, with the addition of the patrol A. When a plan is triggered, we need to test the context of the plan, which in this case, it's always going to be true as long as we have the waypoint coordinate belief, which we do. So this will match to A, waypoint will match to A. Then we go to our belief base, and we see that X, Y, and Z will be the coordinates of the waypoint coordinates of A. So since the precondition of the plan is true, we move on to the body of the plan. So the body of the plan is here on line 19, which is preceded by the left arrow. And the first element in that plan, we add a belief, which is called going. It's just a bookkeeping belief that we are going to the waypoint that we trigger the plan with. And then we execute the action to move to those coordinates. Right, so this action is then translated by the interface to the robot, which in this example we are using MoveBase, which is a library for ROS, or path planning. And what happens in that library is that after the action is executed, there will be a result provided. So in here, in these other 5 plans, we treat the result of that. So this means that these plans will be triggered when the addition of the MoveBase result is added to the belief base. So the number 3 here means it's successful, and the number 2 means it's a failure. So the first 4 plans, they are just one for each waypoint, where we test that if we were going to that waypoint and the result was successful, then means we are no longer going to that waypoint and we can go to the next one in the list. As for the failure, we are just printing here, but it could be something else like failure handling going on here. Now about the verification, the Gwendolyn agents can be verified using a model checker, as I mentioned previously. And the name of that model checker is the agent Java Pathfinder. This program model checker uses a property specification language, which is based in linear temporal logic with additional support for BDI terms. So this is just a reduced syntax that we need for the example that I'm going to show you of the properties. There is a lot more to the syntax, of course. So what this means is that the square here is that it is always the case. The diamond is eventually the case. The right arrow is implication. A is action and B is belief. So here as an example, we have 4 different properties that pretty much say the same thing, which is it is always the case that if the agent turtlebot3 executes an action patrol of a certain waypoint, then eventually the agent turtlebot3 will no longer have the belief that he is going to that particular waypoint. So basically, in other words, this just means that if the agent executes an action to go somewhere, eventually he will arrive somewhere. So to conclude, we apply this to a bunch of different examples. On the top left, we have the example of using 3 turtlebots cooperating in a house environment. Of course, each turtlebot has its own agent. Then on the top right, we have the Jackal robot. Similarly, on the bottom left, we have the Husky with the Universal Robotics 5 arm. In this case, I haven't done the agent yet for the arm, but it works with the Husky itself and shouldn't be too difficult to add the arm. As I've done, for example, here on the bottom right for the Mars Curiosity rover. This is a simulation, and also in Gazebo. And the agent can control the mast, the arm, and all of the wheels of the Curiosity. As another example, there is another colleague of ours here in Liverpool, Matt Webster, which is also a postdoc, and he's part of ORCA. And he has applied the interface to the T-Rex UAV in a simulation using ROS Flight Lab and the Vega Prime simulation environment. And there is a paper with more information about that, if you're interested. So to conclude, we did the integration of autonomous agents with robots that use ROS. This interface can be used to publish messages to ROS and also subscribe to topics. And of course, the AJPF model checker can be used to verify properties about the decision-making component of the robot. As future work, we want to apply it to more use cases. And it would also be interesting to perform some field tests to measure the impact of embedding the agent on the hardware. As for all of the examples that I shown you before, they were all done in simulation. So there is the source code, which can be accessed in these links over here. And that's it. Thank you for your attention.